Hi, and welcome back to the XII Sound channel, and part 15 in the series all about my Project 12 DIY modular analog synth. In this episode we'll be looking at a hybrid module that I put together that I've named the Octivator. The Octivator, two elements to the Octivator. The first one is a very simple op-amp VCO which produces a sawtooth wave and a pulse wave, and then the second part of the module uses a binary counter to provide sub-octave divisions of the original VCO output. But what it does, the Octivator takes the pulse wave output from the op-amp oscillator rather than the sawtooth wave. The binary counter it's a 4040 chip, and it basically, binary counting is counting to 2. So quick demo, you've got 0, 1, 2, 3, 4, 5, 6, 7, etc. Now the thing that makes that useful for synth use and music use is that each of those counts, if we kind of step through the binary registers that are counting, put in a clock signal in, each count would be a half of the clock signal. So you get a half, quarter, eighth, 16th. If you put an audio frequency in as your clock signal, you will halve the audio frequency. If you halve an audio frequency, you drop the frequency down 1 octave. So what I can now do is I can generate sub-octaves of the original oscillator frequency, and what I can do then is I can generate, in actual fact on my module I generate 3 of these and then put them together to a single output, so I can simultaneously have my original sawtooth output and then use the pulse wave output as a clock signal to generate square wave sub-octaves of that original oscillator output. Now, to actually get the binary counter to work properly, you do need something which is pretty close to a square wave. So the pulse wave output on the oscillator design I'm using is actually quite useful for that. I'll show you the actual circuits I used in a moment, but let's illustrate the theory. Now I tested it out by putting a breadboard together with an oscillator and a binary counter, just to kind of see what the results was, what I was getting out of it. So let's have a look at the breadboard system, and you can hear what that theory I've just described sounds like in practice. This is the breadboard test circuit that I put together. Ignore the chip at the top, that's an op-amp. It's not involved in this particular layout. It's just something that is sat in there to basically keep it safe. So what I've got here, built an oscillator out of a 4106. So that's just a basic simple way. It's a hex inverter where you've got a potentiometer between the input and the output, and then a capacitor between the input and the ground. And then down here, this is the 4040 binary counter, and at the moment I'm taking the output from my oscillator and going down to the clock input on the binary counter, and then I'm coming via a resistor here onto the output, which is going, I'm actually using the mixer on Modular to put it into the system so I can record it. So basically what I'm doing, I'm just simply taking the output from the oscillator and putting that onto the output jack. So when I plug the battery power in, what you now hear, let's turn it down a little bit, what you now hear is, it's not what's coming out of the 4040, it's what's going into the 4040, it's what's coming out of the oscillator. Twiddle the pot, change the pitch. So that's what's going from the oscillator into the binary counter. Now what I can do, if I, instead of taking the output from the oscillator, I go to the first division on the binary counter. So this is the first divide by 2. So that should be roughly half the frequency, what should be exactly half the frequency of what's going into the clock input. And then as we move down to the next register, we get quarter or 2 octaves down, and the next one 3 octaves down, or an 8th, 16th. We're now 4 octaves down, and we can keep going, but we basically end up with a series of clicks, an LFO in other words. So that's what's coming out. First division 1 octave, next division 2 octaves, 3 octaves, and so on. Okay. But what we can do, and this is why I'm using a resistor, so that we stop them interfering with each other, what I can do is I can leave the output from the oscillator, but then take the output from the first division on the binary counter and put that onto the output. So we now have the oscillator and its first octave. Its first sub-octave. And what I can do then, I can add to that the next sub-octave. Again, it's tracking as I change the frequencies. Now you can keep going, adding more and more of the sub-octaves. Add the next one in there. He says, put it in the right one. There we go. Get it in the right hole, it actually works. So that's the theory proved, that if I take a square wave oscillator as my clock input, put it into my clock input on the 4040 counter, and then take the binary counter registers out one by one, I can start adding sub-octaves. So that was the theory proved. So now the thing to do was to take that and put it into a panel on my modular synth. So let's go and have a look at how I did that. As you can see from the label, this panel here is the Octivator module. As I mentioned at the beginning, it's it's in two parts. So if you look above the label, this is the VCO. It's a very simple single op-amp design by a chap called Hendrik Gertling. I got it off from one of the electronics forums. I'll put a link down in the description so you can find the schematic. But I built it onto a strip board layout, which looks like this. And again, like I say, a very, very simple circuit. In Hendrik's design, it's actually designed to run on 9 volts, which is fine. I'm sure it would run on 12 as well. You might get variations in pitch, but it shouldn't make too big a difference. And it's a single rail supply, obviously. And then if we get back to the front panel, the controls, we have a pitch control, then there's a sawtooth output and a pulse output, and then a CV input. On the breadboard I used a 4106, but this gives me better control over things like CV, plus I've got a useful saw wave output, and I can use the pulse as a driver for the binary counter. Talking of the binary counter, you go below the label. Very simple, in and out. It's the same layout that I demonstrated on the breadboard, and so the circuit diagram would look like this. And what I've done, I've actually taken the first 3 registers, so I've got divide by 2, 4, and 6, counting in twos. So I've got the first 3 octaves basically, first 3 sub octaves, as well as obviously getting the output from the original output from the oscillator. And when I put that, I put it on a separate strip board layout, which looks like this. And then I wired the two, built the two together onto a panel, and so it kind of, the finished thing looks like this. But the key part about the way I've put this together, you could actually have done it all on one strip board. But if we go back and look at the front panel again, the way I've done this is I've used switched sockets. They're all actually switched sockets, but the key ones are the pulse out and the octave divider in, and the switch tab of the pulse out is wired directly to the switch tab of the divider input, which means with nothing plugged into either of those, they are connected together. So in its basic format, you get the saw output and you get the 3 sub-octave outputs automatically. As soon as you plug anything into either the pulse or the divider input, it breaks that switch contact and they become 2 independent units, which can be useful as well. So there you go. Very simple really, in terms of its design and layout, and very easy build. But what does it sound like? I will say, before we move on to what it sounds like, I've just remembered the one thing I did find, and I don't know why this happened, but when I plugged it into 9 volts, which is kind of what the circuit was designed for in the first place, worked fine. Plug it into a plus 12 volt supply rail, the VCO still worked, but I couldn't get the binary divider to work. And I don't know why, because it's supposed to take up to something like 20 volts. So 12 volts should not upset it, but for some reason it just didn't want to work. Whether I got some wiring wrong or wherever, I don't know. But when I plugged it all back into 9 volts, worked perfectly well. And since I've got plus minus 12 9 volt and 5 volt in this system, it really doesn't matter. I can use whichever voltage suits the panel best. So it's actually, in this system, it's running on 9 volts, but in theory it should run on 12. Anyway, enough of my rambling on. The important thing is, what does it sound like when you wire it up to the rest of the modular synth and start playing? Let's go have a listen. I've set up a simple patch here to demonstrate the Octivator in its standard configuration. So this is the sawtooth output from the Octivator's onboard oscillator, and that is going into the input on a low pass gate, and the output from the low pass gate is going to one channel on the mixer. And then in the standard configuration, the pulse output is automatically connected to the Octivator input, so the pulse wave from the oscillator is going into the clock on the 4040, and the output, which gives me the 3 octaves, 3 sub-octaves, is taken into a second low pass gate, and the output from that goes into second channel on the mixer. The pitch of the Octivator's oscillator is fed a CV signal from a simple sequence I've set up on the beat step. The gate from the beat step goes into my gate buffer, which allows me to split the signal and use it to drive both CVs on the low pass gate, so everything is kind of synced and in time with each other. So if I start the sequence running, what I've got dialed in on the mixer, all you will hear first of all is the oscillator's sawtooth output. So now if I dial in the output from the Octivator, what you will get, the pulse output will be tracking with the saw output because it's the same oscillator, and then you will get the 3 sub-octaves starting to come in from the Octivator. So that's now the sawtooth and the sub-octaves. Turn the sawtooth out again. And you should be able to hear the difference in the wave shape, because the Octivator is generating square waves as opposed to the sawtooth, which is the main output of the onboard oscillator. And that's it. That's the basic configuration, the standard configuration of the Octivator, and that's the output you get. What I can do, if you want to hear what the pulse output sounds like, this will now have disconnected the Octivator, so all you will hear is the pulse output. Of course, I've still got the sub-octave dialed in, but by plugging into the pulse, it automatically disconnects the binary counter, the 4040. And there you go, 4040 comes back in. Now if we were to plug anything into the Octivator, you're getting a bit of a click, but you're not actually getting the octave outputs. That's just the very basics. You can do a lot more with it, and you can also use the oscillator and the Octivator independently. And the thing is, it's a modular system, so you can patch things around. So yeah, opens up a whole new world of possibilities. But there you go. That's the basic Octivator. I've shown you the theory, I've shown you the circuit diagrams, I've shown you the strip board layouts, I've shown you how I put it together, and you've heard its basic operation, but that's just the start. You can really do some great things with this. It opens up your old patch possibilities. So yeah, you've got everything you need. So go on, have a go, build your own.